My name is Ranga, and today we're going to see how to elastically scale your applications without losing performance. First, a little bit about myself. I started my career at SGI or Silicon Graphics. Not sure many people here will know who that is or what that is. Okay, there you go. So we built really large scalable servers amongst other high-end graphics products, and I was one of the original kernel engineers working on that. From then I moved on to high performance network switching for data centers, very high throughput fabric that got deployed in every data center in the world at that time. And then about 4 years or so, I've been at Avi Networks. I'm co-founder and CTO at Avi. What we build is scalable, elastic load balancing, which still continues to be a big pain point of how to scale your applications. In the next few minutes, we will see how applications are still predominantly deployed in production today, why that is changing, why that has to change, and what are some ways by which you can actually change those. At any point during the talk, you have a question, just raise your hands. We'll also have maybe 10 minutes towards the end of the presentation for any questions, and I'll hang around after that if you need it. Okay? All right, so this is how almost all applications are deployed in production today. Still monolithic. It's usually a few tiers. There's a presentation tier over here. And then there's a application tier, which is a monolithic application tier over here. And then there's a persistence tier. And between all of these, you have what are called as load balancers. These spread the load for incoming connections across different instances of these applications. And a single stack here represents a data center. And the way applications are scaled today are completely manual. The administrator looks at incoming load, monitors that over a period of weeks, months, maybe. And then if he or she sees an increasing trend, then schedules an outage window, increases the number of instances. If it's the opposite, then he or she decommissions a few instances. This completely ignores things like how the application usage changes within, for example, days or weeks, or sometimes even, as in the case of, for example, retailers, you have enough capacity to handle load just for 1 week for the entire year. The rest of the year is just sitting idle. This pattern continues to occur amongst many applications in retail, in service providers, in the gaming industry, and so on and so forth. Bottom line is that you have severe over-provisioning of your data center resources. CPUs continue to run sub 5% or lower. That's a huge cost. Now, if you want to provide some level of availability across your data centers, then your choice is to deploy your applications across data centers. Once you do that, then you need some way of directing traffic to different data centers. Now, this can be based on availability. If one data center goes down, all traffic is directed to another data center. It can also be based on performance. For example, you want to direct all users in the East Coast to data centers in the East Coast, and vice versa. And we'll see some of which all of this is changing as some big trends are happening across both the development as well as the infrastructure world. The two big trends that are happening, and we will see how these are affecting especially performance and scale and elasticity, are microservices and the advent of the cloud. Now, I'm sure all of us know what these are, and we are part of some of these transitions. In the next few slides, we'll see how specifically these trends not only make it possible to build more elastic infrastructure, but it also makes it important to be able to do that. Okay? So the first trend is microservices. What is it exactly? So we saw the monolithic business logic in the previous slide. So that is this big blob over here. This is decomposed into smaller services or applications. So each application here, for example, is a small micro application or a micro service. And I was chatting with someone who's a big content creation company, and recently they are actually going through this motion. So all their applications are built as big monoliths, and they are suffering because of that. And the reason that they're suffering because of that is it's very hard to change things and roll them out quickly enough because of the nature that they are big monoliths. They need to undergo a lot of testing and so on and so forth. So the first thing, big advantage of decomposing applications, of course, allows you to rapidly change any individual service. So since these are somewhat loosely coupled with each other, changes in any single service affects just that service. And so you're able to rapidly iterate over that service and roll out newer features, faster features. But that also doesn't mean that you can actually break those services. So you need to be able to test those services. But there it actually gets simpler because it's a smaller service. It has fewer number of test cases. It should be possible to run those test cases faster and build a test pipeline for that faster. The third aspect of doing this also is that you can now individually scale every single microservice in and of itself. Some services by nature are resource intensive, require a lot more performance and infrastructure. Some of them are not. So it allows you to scale them independently. And it's actually this last aspect of this transformation that we will use today to be able to dynamically scale, elastically scale performance. Now, the first aspect of being able to scale this is each instance of a microservice is ephemeral. It is replaceable. It's treated as cattle, not as pets. And even if it is stateful, then it is transactional. So the impact of bringing down or creating a new instance or adding an instance other than affecting performance should not affect the correctness of the application. And this is quite important to be able to elastically scale the microservice. So it's really this transformation from a monolith to microservice that allows us to rapidly add or remove capacity, excess capacity, when you really don't need them. The second aspect is how do you actually do it? So you want to measure load. You want to see how much capacity you have, and you want to match capacity to available load. The next question is, what exactly is load? Load can be resource-based, just commonly CPU, memory, storage, and so on and so forth. Or it can be performance-based, which is the actual latency seen by the users or another service. It could be total number of open connections and so on and so forth. Certain things work well for certain applications, and you need a bit of flexibility in which service fits well with which definition of load. Once you have that, then you essentially want to constantly keep measuring your incoming load, deduce the available capacity for each service, and you want to be able to match the capacity to load. So in this graph, if the green line represents capacity and the red one represents load. So load varies, it starts low, goes up, comes down. You want to always make sure that the green line is above that of the red line, so you always have excessive capacity. Is that all? Are we done here? Actually not. So if you see here, there's a little bit of a problem where the green line dipped below the red line. What that represents is actually lost users. So because you did not have enough capacity, you actually lost users. You suffered some performance. You definitely don't want to do that. So a next step is it would be great if you can actually increase capacity before the load actually spikes. So most applications follow a certain pattern. If it's a business application, it usually goes up during business hours. If it is an entertainment application, a streaming application, it goes up during evenings and weekends, or other kinds of data patterns. So almost always, if possible, you want to be able to learn the load pattern of the application and do your predictive scaling in such a way that you always have excess capacity. So some safety valves when you want to do this scale is that you want to be able to smooth out the auto scaling events. What that means, you want to be able to set some thresholds and essentially say that I don't want to rapidly fluctuate around how much capacity I need. You always want to be able to scale aggressively or increase capacity aggressively, but be more conservative about when you're actually reducing your capacity. A third one is there can be corner cases, error cases, where there's an outage and incoming load appears near to zero, but it is actually not true because when the outage heals itself, there's a lot of traffic that comes in, and suddenly if you scale down, then you will find that you will have a real life problem because of that. So you also want to be conservative because of that. So you almost need some safety valves when you build this logic, but these are some guidelines that you can definitely follow and effectively be able to scale your services. Now, what we have done so far is we've taken an application running within a region or a data center, broken that down into individual microservices, and be able to elastically scale every service or the application itself as a whole. Is that all? Not really. So the next aspect of it is why do you need to do it, and what changes because you now are dealing with a more automated infrastructure, which is what clouds actually bring to the table. So the other major trend where applications get deployed is moving rapidly from the old sort of traditional way of provisioning VMs to a more a self-serve model, or it could be API-driven model, where you have access to infrastructure as you need it, whether it's in your own data center or it's in the public cloud. Now, public cloud offers several choices. For shrink-road applications, you probably want to go with the SaaS. But if you're going with a PaaS and you want to avoid lockdown of the vendor, then you probably want to go with IaaS with some other choice of a PaaS like Kubernetes, or there are plenty of them out there. But regardless, the point is that the infrastructure is elastic. It's available to you instantaneously when you need it, and it's also automatable. And we'll see why that matters. So clouds are both a motivator and also an enabler for elasticity. Why is that? It's a motivator because for the first time, probably, we have a breakdown of the costs of infrastructure. We know exactly how much we're spending on compute versus storage versus networking versus other services. We can also put a figure around every application and see how much we're spending for prod versus test dev. And once you have that kind of visibility, you almost always want to optimize for it. That's just the way world works. That's just human nature. And so it gets highlighted as a cost, and you want to be able to optimize for it. So that's why the cloud is also a motivator for getting better utilization from your system. It also allows you to deploy more applications. So it's all the more important to get better utilization for all that infrastructure cost that you're spending. It's also an enabler because you don't have to rely on a human speed to actually get access to infrastructure. You use APIs, you use or other UIs to instantaneously have access to infrastructure. So it's also a big enabler to build an elastic infrastructure. And the next few slides, we'll see how a lot of enterprises today are actually evolving their public cloud strategy from a deployment and a traffic management perspective. So this is probably the most common example, well, almost everyone starts, where you have all your traffic still coming to your data center, and you're using a region of a public cloud as an extension of an additional data center. Traffic still comes into your primary data center, and you're using your public cloud mostly for workload and for either production workload or even for dev test, and you usually connect them with the direct connect. This often evolves into second model, where users are actually coming into both the on-prem data center that still exists, as well as some regions in the public cloud. And that's sort of the two common models, evolutionary models, where it start with one and then evolve into two. A couple of other patterns that you can also see is that companies that have a global presence across the world, or even across regions within the country, can now use public cloud regions to improve performance that their users and clients see. The closer your TCP connection gets terminated to you, the faster responses that you will see. So another example here is a payments provider who is using GCP's regions as POPs almost to terminate client connections as close as possible across the world. Other pattern is around you have, for example, retail. There's a lot of branches, and you again want to be able to terminate connections within those branches for users as close as possible, and then backhaul everything, all the traffic into the cloud. So the first two patterns are probably the most common, and we will talk in the next few slides, and we also have shown a demo on how that can change, how you can adjust and evolve your elasticity and in your traffic. So the most important thing that we saw briefly touched upon in the first slide is that you want a way to be able to direct traffic across regions. The component that does that is called a global service load balancer. If you're using AWS, it's Route 53 that does that for you. It used to do two things before. It used to direct traffic based on availability of the application. It also used to do that based on geolocation of the users. The idea being that you always want to send users closest to where they are located, provides them the best performance. There's a third aspect that people are using it for, which is it's also an effective tool to manage your cost. If you have a data center and you already paid for that facility, and you want to maximize that capacity, and you want to use the cloud, for example, as a burst vehicle, then you want to set up policies in such a way that almost all your traffic initially goes to your data center. And when that gets close to saturation, then you want to send your connections to the public cloud. So that's a sort of a third aspect or a third technique that you can use to drive elasticity and manage costs across your data center. And the last one is you almost always want to monitor performance. You want to be able to tie that down to your cost, what you're paying for that performance. So we covered how applications getting deployed across the public clouds and how you can use some traffic management policies to effectively direct traffic to the right region. Is that all there is to it? Fortunately, no. A critical piece, at least what we find in this, is what is called as the load balancer. Because it's the traffic director, it's the traffic manager that decides where the traffic actually goes to. Here's an example of a compute cluster that's quite dynamic, quite elastic, and you can create as granular capacity as you want, and you can give them to your applications. On the left, you have the load balancer devices that are still static. You still have to buy capacity for the peak. So if you have 1 million users who will go through your system on Black Friday, then you have to buy capacity worth 1 million users. and you have to keep it there. So that's been the model so far. These are very expensive devices. So how do you scale them? Well, see, a common technique for scaling them is also exactly the same microservice pattern, where you break down a big monolith into smaller pieces, and then you manage those smaller pieces. But before you do that, when you break down the monolith into smaller pieces, how do you still offer an aggregate performance for that single application? If I had a single application that has 1 million users that come in, how do you still provide an aggregate capacity with a number of smaller load balancers? So there are fundamentally 3 ways to scale a load balancer. You can do it with DNS, you can do it in a hierarchical way, you can also do it with the routing. DNS works in this way. Every user goes to www.facebook.com. He or she gets an IP address. Now, this IP address can be different for different users. So depending on that IP address, that user goes to and connects to a smaller load balancer. And that's exactly how ELB works in AWS. The advantage of this approach is that you can keep scaling this, and there's no limit to it, and you can keep going. The disadvantages are well known with respect to DNS. DNS gets cached. When one of them goes down, then there's a TTL, and for that duration, those users are going to suffer some performance problems. Next way is you can actually do it with the hierarchical load balancer. You can have almost a stateless load balancer in front, which just looks at and directs connections to a more stateful one as a tier 2. This scales sufficiently, but there is a limit because there's a single point where all traffic comes in. It's simple, it's effective for smaller applications, but it doesn't scale elastically, it doesn't scale linear. The third technique is when you actually have your routers do the work for you. Routers are very high performing devices. They are built with ASICs. They offer hundreds of gigabits, multi-terabits in performance. In this case, you actually program routes in your upstream router, saying a given IP address has 4 next stops or 32 next stops. And essentially, then the router will send different flows or different users to different load balancers. This is the most effective technique. It's also the most transparent technique. The one downside is that it's not always possible to do this. If it's possible to do this in your own data center, it's possible to do it with some public cloud providers like GCP or Azure. It's not possible to do it in AWS, for example. So you definitely need different sort of tools for the trade, depending on which one you're solving. So, but let's assume for a second that you're using one of these techniques to actually scale a group of smaller load balancers into a larger load balancer. Once you have that in place, now the problem looks a lot like what we know of. So let me just build it out here. So on the left here, we have our big monolith, which we have now broken down into smaller micro load balancers that we can now spread out across the infrastructure, deploy them as VMs or as containers. And you can manage all of them with just an API endpoint that you use to program. So this pattern of decomposing a big high performance or a big blob of infrastructure entity into smaller performance works well here for load balancers too, assuming that you have a way by which you can aggregate their performance and actually be able to scale this. Now, these smaller pieces, the question arises, how do they perform? In fact, they perform very well. Most modern microprocessors, starting at least maybe 7 or 8 years ago, they provide very adequate performance for almost all classes of applications. A single core today can start with about 2,500 to 3,000 SSL TPS, and you can add cores to your microload balancer. You can also scale them out, as we saw, across multiple of them. In fact, we just to demonstrate that it is possible to do this, we recently ran a test in GCP and scaled a single application or single IP address to over 1 million SSL transactions per second. It is a fact that there are very few applications in the world that need this kind of performance, but it's to prove a point that it is possible to do it with just no specialized hardware or anything like that required for it. So to summarize, let me finally show a small sample application. What it is I have traffic coming into my data center at a certain rate, and just at a click of a button, I'm able to actually move and shift this traffic to public cloud. And this is but an example that you can build on with other more rich policies to say that I want to be able to elastically move my traffic around. So what I have here is a sample application. It has two sort of services, one running in the data center on vCenter, as a matter of fact, the other one running in AWS. And I have a single GSLB service here that's directing traffic to both of these. And so you can see here it's about a factor of maybe 25 or 30 in terms of the ratio of traffic that's being directed to my on-prem versus AWS. Now, if I needed to change it, all I really have to do is just simply control a ratio here that controls how much traffic goes to my data center versus my public cloud. And you will soon see that the traffic ratio here will converge more towards a ratio of 1 to 5. And you can, of course, play with it and do it even more. And you can also create policies to be able to automate that. You can say that if the on-premise application is nearing its capacity, then you can change the ratio or bring in more capacity. As you bring in more capacity in the public cloud, you can actually skew the ratio to say more traffic goes to public cloud. I can move traffic the other way too. So in a nutshell, essentially what this allows us to do is we are able to increase the capacity of a single microservice running in a single data center, also able to actually move traffic around across data centers or across regions. And there's some lessons that we have learned over a period, which is that as an indicator of load, CPU and memory works well in some cases actually does not. You need other metrics like actual performance in terms of latency and so on and so forth. The other thing is, in real life, it's actually quite remarkable how much you can consolidate applications. We have worked with customers who have been able to consolidate sometimes by a factor of 2x, 3x, or even 4x without having to do anything. You just set up your auto balance policies, and it automatically uses the minimum number of instances that you need. The other thing is, of course, you will see bills. Previously, the data center cost was a sunk cost. Nobody cared much about it, or said the business is more important than the cost. But now, you'll begin to see big bills from your public cloud provider, and it will become an important business driver to be able to squeeze costs out of that. And lastly, a global traffic management policy also allows you to avoid lock-in to a single public cloud provider. You almost need an arbitrage to say, I want to be able to actually move traffic as I need between, say, AWS and GCP or GCP and Azure, and so on. So this also gives you the flexibility to be able to do that. Of course, you also need other things like tooling and so on and so forth. But this is a critical piece of being able to do that. Right? Thank you. That's all I had. Questions now, please. Yes.
You talked about using routers to do some load. Can you talk a little bit more about strategies that you use?
Yeah. So the question is, how do you actually use routers to effectively scale a load balancer? So routers, typically the way they work is you program a route which is saying to reach this destination, this is the next hop for the destination. So in this case, if you actually had a single load balancer, a single IP address for the load balancer, and you want the router to send flows to 4 different entities, then you'd program 4 routes. You'd say for this IP address, there are actually 4 next hops. Each next hop points to a load balancer instance. That's all there is to it. Once you actually program such a route in the router, then it will automatically do something called equal cost multipathing, which is it will send a single flow, which is a TCP flow, which is between a user and a specific connection, and it will automatically send flows across your 4 load balancers. Now, you need to be able to program that route, so that means you need to have access to the router, which is if you own the data center, of course you do. If you're running the public cloud, then you don't directly have access to the routers. So both GCP and Azure actually provide API access to the routers. So you can actually call an API, and it'll do exactly the same thing for you. So that's been very effective. So even in the sample that we showed where we achieved 1 million SSL TPS, is exactly what we did in GCP.
So would you divide that according to source IPs?
Yeah. So a given connection is identified by what is called as a 5-tuple, which is a source IP, destination IP, source port, destination port, and protocol. So when an incoming connection comes into a router, if it has multiple next hops for it, the multiple next hops could be other routers as well. So routers automatically perform a form of load balancing. So they send each packet belonging to a flow on one next hop only. So there's no reordering, there's no rehashing and so on. So it works quite effectively. Yeah. Any other questions? Yeah, sure.
So you mentioned Azure and GCP. Have you looked into Roku at all?
Actually, no, I haven't looked at them. The other ones that we have looked at is also SoftLayer and Oracle. At least as of now, they don't offer any access to those as well. And I'm not sure of Heroku. Not sure of that. No. Yep.
Is there any kind of expert scripting we can do to decide based on threshold levels direct the traffic to different regions?
Yeah, exactly, right. So the question is, can you actually script this and automate the traffic direction? Absolutely, yes. So the whole idea is you want all of this to be automated. So you just want to be able to set some policies, and then you want that data to be driving your scripts. So your policies can be based on time of the day, connections, cost, availability, anything. And so yeah, and then the whole thing is automated, and then you want traffic to be directed based on the policies, running a script essentially in the background. Yeah. Sure.
So you talked a bit about ASCII, like you have to plan ahead for ASCII, like say your worst day is Black Friday.
Yes.
You have to
Yeah.
plan for that. I believe that cloud providers now have actually responded to the community and are doing fungible timeshare style capacity where you purchase the capacity.
Yeah.
If you're not using it, you give it back to the cloud and you request it back when you need it.
Yeah.
So that's starting to change that a little bit in terms of costs.
Yeah, definitely. Yeah. So yeah, that helps. Having an auto scale policy helps. Having some cost management helps. And the other thing is also I've seen a large company is about 3,000 developers. They've gone to a level of even optimizing their dev instances. So previously you would give a VM and it would, if you had 3,000 developers, it doesn't matter where they are, there would be 3,000 instances running. So now what they're doing is they have some developers in the US, some of them overseas, and then based on the time zone, they're actually swinging that around and repurposing them for overseas developers.
Yeah, we rolled our own version of that, and now Azure has test labs that will stand up VMs and shut them down when you're done.
Nice. Yeah, nice. Yeah. You got a question?
How do you scale the controller cluster automatically?
Yeah. The controller is also developed as a microservice. So there are some parts to it, like the control plane, that is not very heavyweight. So that's you don't need to scale that up or down too much. The other thing that it also provides is the analytics. That is definitely something that you want to scale. So you follow the same techniques. You treat them as an application, as a set of microservices, and depending on the requirement of that microservice, whether it's heavy on storage, whether it's heavy on throughput, whether it's heavy on CPU, scale them independently. Yeah. There's one question in the back.
Yeah, coming back to the DNS load balance.
Yeah.
The pros, you said that the con, you said that the TTL during the can't you change the TTL and update the cache to
Yeah. Yeah, good question. So the question is about DNS and so the TTL issues associated with it. That's what AWS does. The TTL is 60 seconds. Unfortunately, DNS caches sometimes ignore TTL, or they are configured to ignore TTL, and instead just use a configured value. So you could have a lot of the DNS requests also come from either service providers or from your corporate. So when from my MacBook, I'm actually trying to resolve Google. This goes to the service provider's DNS resolver, and what Google sees is actually the service provider as the DNS requester. So the service provider has configured a TTL of 10 minutes. Then doesn't matter what the response from Google says, it will keep it in the cache for 10 minutes, and that's what I'll see. Yeah.
What kind of replication techniques do you have for for client on certs, and also does the load balancer support stabling?
Yes, it does.
You probably can't get a million TPS stabling, or what?
Yeah. So it would be hard to achieve that. In most cases, the practical scalable cases use CRLs. There are some very specific cases where you need stapling. Fortunately, the performance requirements for those are low because now you're dependent on the CA's performance. Yeah. Okay. All right. Thank you. Thanks for being here. Thank you.